to like various aspects of machine learning, starting from decision trees and all the way up to transformers. And he also gave us some ideas about how these models can be used, some possible applications of these models in the domain of weather and climate. And I think now he is going to give a detailed demo of such applications in a couple of use cases. Over to you, Rajib.
So good morning. So I'll start yesterday's by recapping one or two words, like the machine learning model added two new way of looking in it. The CNN and the transformers. What is that? CNN filters you image in the space. So if you have a grid like this, it connects you, the kernel filtering connects you to the nearby grid. The other part attention mechanism gave is if you have a stack of image like this, how the past is related to the present. So these are the two, and these two concepts, it's not that it's not known already, but it has been implemented in a framework when it is very highly scalable, starting from a single time series to a billion of time series or a billion of image, you can process it quickly. So that's the advantage of looking into it. One is that it has been quantified in a way that you do not need to look into the very individual physical process of the system. And the other thing is it can be scaled using it. And the more you get the information, the better. Now, let us start with the classroom problem where I stopped. Okay, I have two lectures, but if I don't finish the second part, I think the lectures will be there and you will be able to get it there. But still, I want to go slow for the first part because that's what it's how you are thinking should develop, how you are going to apply a model like this. So we have now the domain of application is Indian monsoon rainfall, which you know is very important, and other things. So another reason is that you know one thing that in this type of spectrum, low frequency intraseasonal oscillations, which are evident in the time series, does not always fit into the wave number frequency spectrum diagram. So these black lines are the diagrams which are the theoretically predicted curve. This is the Rossby wave, this is Kelvin, this is this. This part does not always fit to the diagram. So the point is, it's a, however, since you get it with the data, it's always useful to get a data-driven model to learn those features better way. So this is the Indian monsoon rainfall. It's a data long back created. What I am trying to see is that this data in the subseasonal scale, initially you have a set of rainfall data for day you have collected, and now you want to label this data. Okay, labeling means what? I want to study how the day-to-day rainfall varies over Indian region. So I want to label this data in a way that there would be, now there is active phase, there is a break phase, there is active phase, there is break phase. So there is a translation going on like this. I want to understand. So as a classroom problem, this is one of the simplest but well studied. So I am taking this thing. So look at this diagram where you see this is rainfall, where you have positive and negative values. Here you will have a system where lag zero means when you have the maximum. So there is a time series like this. This is the maxima here. When there is a maxima, you see strong rainfall pattern here, and there is a strong negative rainfall. So this is a quite famous diagram if you are studying a monsoon intraseasonal oscillation in the system. Now, what we are trying to do is we are trying to, if we just go back in time, okay, so 0, -5, -10. So you see 25 days back, there is an opposite pattern working here. And as the time progresses, this pattern becomes stronger. It moves northward, it moves, settles northward, now it settles. Then again, the opposite pattern started forming, which again, so this is the pattern of intraseasonal oscillations which is going on in the Indian monsoon, repeated low frequency, slow intraseasonal oscillation. Now we all like low frequency because yesterday one paper came from another lecture that it says that uh, low frequencies are better to predict because our predictability limit is like if a system has a lifespan of 7 days, you can maximum think of predicting 7 days ahead. So this was some empirical rule. It was developed long back in the 80s. I forgot that paper's name, but yesterday it was shown. So if I get a low frequency oscillation, it means that I can predict it in the long range. So we all like long range predictions because that's what we need for ahead of this thing. So remember this pattern we get for Weller, the rainfall, Weller, anything, and it is superimposed over a seasonal mean pattern. So there are set of oscillations going on. One is the seasonal mean. Above the seasonal mean, you have the subseasonal mean, and those oscillations every year looks different. Some year is very strong, some year is weak. Sometimes it is extended, sometimes. So this is extended active, extended break, and now these things are very much important because these are. So if you have a long break like this, you will face problems in the agriculture. Now, idea is to predict these transitions. You see how quickly it transits from one peak phase to another peak phase and how it slowly moves from here to here. So all these features are very important if you are trying to predict the rainfall over, and these are the things which people want. You need to predict something, these transitions, the slow transitions, the fast growing systems, the slow growing system. These are the things people want. So this is why it is so important to study intraseasonal variability in the Indian monsoon region or in the tropics. So, and the second point is that it's not theoretically available. The spatial structures, you constructed it from maxima to going back. Now you know that if you have a system which is very noisy, rainfall is very noisy. So this is based on filter data. It looks so nice because and why you should apply a filter if you have a, so you should be able to get the pattern very easily. So, and these are some of the examples from different years where I show that actually how noisy it can be, patterns can be, and how sometimes this red means it crossed some threshold which are called break, and so green is, so you see the active phase, sometimes the rain. One another point is rainfall gives very high amplitude. So one side of the oscillation is very high, another side is low. This is very interesting for monsoon interseasonal oscillations. Normally in other systems, you do not see like this. So there are a lot of interesting features like this. And there is multi-scale system. You have a lot of inside cloud bands of waves which are moving inside. So such a complex systems we are trying to model. So what we are trying to do here as a classroom problem, need to catch the observed pattern in a better way and need to analyze the simulations. Okay, so there are linear methods available, but the point is that each of, since these patterns are of empirical in nature, you don't know that each of these methods, whether there is a nonlinear thing, is affecting your results. It's good to verify using different methods. So we will think in the perspective of machine learning tools. So in a machine learning tools, we are going to get this thing. So what we will try to do, we'll do a dimensionality reduction in the sense that we'll get a few simpler patterns which can explain the thing, and the other part is that the pattern recognition. So which are the most important? These are closely related, but application based on application, these are all, so you can do it. So before going this thing, I want to show a linear result which is called EOF. So you know how do you calculate EOF? If you have done it already you know that we take any variable, we construct the variance covariance matrix, then multiply the transpose of that, and then we create the eigenvectors, simple eigenvector, and then we get the pattern. So this is one. The problem with EOF analysis is that these patterns has to be orthogonal. So these are all linear transformations. These are patterns has to be orthogonal. So what happens is these are orthogonal patterns. These are orthogonal. It does not guarantee, and this pattern expresses very high variance. This is arranged in the order of importance. Now, point is, it's not always true that the physical system will give the most dominant pattern first, then this. And this linear, strong criteria of linearity, you have to make it orthogonal. So if you see the literature, these beyond 1 or 2 EOFs, these are mathematically irrelevant values. Okay, these are constructed based on mathematics, but this may not have physical. It does not mean it is always having that thing. For example, if you see El Nino type of system, El Nino Modoki structures, those are constructed based on higher order EOFs because they find the spatial analog, actual analog of those. That's why they are physically relevant. But it's not guaranteed from the data analysis perspective that is going to be relevant. Okay. So these are the questions which are, so what is the pattern of monsoon rainfall, subseasonal variability, then spatial structure and life cycle, and how the large scale factors participate in shaping the rainfall. Now remember, if you have a rainfall pattern, you get a rainfall pattern from rainfall data, label data. It's not that, I mean, okay, rainfall should organize in terms of rainfall. There's nothing. The point is, if you see the dynamical models, you have 5 equations where U, V, omega, T, and Q. So what, and you do not get a rainfall equations directly. You maximum get a moisture equations directly, right? dq by dt, which is a moisture equation. You get the equations of continuity, you get everything. Now, the point here is that rainfall is arising as a result of some parameterization. Okay, we know that convective parameterizations give convective rainfall. Large scale parameterization gives the large scale rainfall or stratiform rainfall, like that. The sum of the rainfall is the sum of all those processes which are basically derived based on this pattern. So the point I'm trying to construct is, so rainfall is a function of U, V, T, Q, and n number of variables here. So how do I verify that a pattern which I am getting from this is actually matching the pattern which we derive from rainfall? So this is the more general theoretical problem, that I have a set of vectors and those vectors are linear linked in such a way that it gives rainfall. I need to model that pattern. So what I did that time was, so I have answered these questions. So what data we need? The data we need are those variables which are useful in the dynamical models. Okay. Now unsupervised we should prefer, because as I said, that is essentially unlabeled data. I mean, monsoon, it's difficult to label a data every day that it is basically. So, but we will try to label it based on how it is arising. Okay. Now, it's also fundamentally connected to the Matsuno-Gill problem. Okay, so it's a free or forced oscillation. So monsoon rainfall patterns sometimes evolve on its own. If you see, sometimes it's evolving like a annual mean, sometimes it's evolving due to low pressure system. So there are a lot of things involved. So when we have this complex multi-scale structure, sometimes the rainfall of 10 days can be correlated. Sometimes rainfall of today and tomorrow are not correlated. So such different scales of long range pattern matching is there, and extremes develop. Of course, you know, those are the things. So, so based on this, what I did is, that time I took, because that time the graph networks were not very popular when this work was done, and it was a close popular tool, the self-organizing map, which is the unsupervised learning technique. What this thing does, you take a set of higher dimensional vector, then you project that vector in a 2-dimensional space in such a way that these patterns are actually related to the topology is conserved here in the so that means, in other sense, if you have an active rainfall pattern here, you will have the break rainfall pattern, which will have low rainfall pattern will be situated in the opposite in the node. And so each node here has a neighborhood relationship. So there is a neighborhood. You won't get a relationship where the neighborhood relationship is not violated. So the training is done in such a way that we have a neighborhood relationships between these nodes. So what, as I told you, that I am not interested in getting rainfall to rainfall pattern. I am interested because dynamical models have dynamical variables like U, V, omega t. I took a set of 10 index. Okay, so these, now you can create a subset of it. You will get a lot of different things. Now the idea was to see that which of this set of index you can add multiple of this match based with the linear pattern, because remember that time when I have applied the machine learning concepts were still seen as a means data churning methods additional. So if it does not conform to linearity, I see Ashish Chattopadhyay still trying to say that it's matching with the linearity problem, that my models are not that different. So these aspects are actually based on so much huge applications has gone. Nowadays, nobody is seriously asking those questions except for the theoretical background. But there was a time that you have to get a set of patterns which match with the linear pattern. So exactly I am showing the results which actually matches with the, you can add in a huge number of patterns. Nowadays, computation is not a problem. You can add lot of less patterns, and you can try different combinations to see what new patterns you're getting. So as I said, these are the index, and these index selections is based on some physical considerations, like this is the rainfall, the black strong curve, and these are the variables which are following the interseasonal patterns here. So these index are not like something I took a variable which is not related to it. So some empirical considerations we give there. And so what is the training that, so let me explain it with the graph actually. So I have a set of patterns here, input data, and these patterns, we have a set of clusters or nodes. What is happening is I am comparing the Euclidean distance here with the input vector, so which is say 10-dimensional vector, to the other Euclidean distance of the, so I got, so initially it is a starts with a random white noise vector. Then as I input it, so first suppose this vector gets most strong from closest from there. So we'll say that we change that vector weight from the random to the slightly changed value here. And what SHOM does is it's a like cooperation and competition. So it means that it not only changes the vector here, it actually takes a neighborhood of the variables and also changes the vector neighborhood functions also with a slight less value. So the strongest pattern learning occurs here, but a set of neighborhood is also considered for pattern learning. So that's one thing which is very important, because you are not, so you remember, so my objective is that I want to get a clustering where similar features are clustered in the same side, opposite features are clustered in, so that it looks like a wave-like of patterns. Okay, k-means clustering does the same thing, but it does not give a neighboring function. That's the difference with the k-mean cluster. Once we do this, now some basic results. So suppose I have a rainfall mean and standard deviation, okay, central India for a set of days, and I do the clustering. I see the node locations here. This is a simple two-dimensional variables I have showed, because if it's a vector, you cannot see. So suppose this is the dark shades, the light shades are the actual data point, and these are the clustered values. So you can see that how clustering occurs as far as the data, where you have more nodes allocated here, where there is more data, less nodes allocated. The other application is filtering. So if we have a filtered data here, and the dotted line is the actual rainfall, you will get the filtered value here very well. So that is one very important thing. Now, if you increase the number of nodes, this is one set of nodes. There are all unsupervised learning, you have to decide on the nodes. So if you increase the number of nodes, then you will have this will much more be smoother, and you will actually regain the data with the help of some filtering. So what I'm trying to say is the patterns which we are getting are doing the clustering as well as the filtering. Now, if I plot the rainfall, one important thing is every day is clustered into these values. So you need not have, now you can forget about your input vectors. Now what you can see is you can plot any variable you want, and you see that there is a pattern like this and there is a pattern like this which is clustered. I am showing a 3x3 cluster. So this has the high rainfall phase, this has the low rainfall phase, and slowly rainfall evolves like this. And this evolution, if the CMAP data, if you see, it matches with the linear evolution. Now remember, the objective was to see that my other empirical statistical analysis is not violated in this analysis. So I am showing you the result which matches there. But if you change the number of clusters and other things, it will lead you a lot of different and interesting things. I'll discuss a few of them. Okay. And most important thing is every day we have a set of clusters, okay, like this, which is associated. And if you plot any variable, you can now plot any variable. You need not be restricted to the vectors which are used for clustering. So you will see the patterns are matching with the monsoon flow, which we get from the linear. So the point is that your clustering is better for all variables. You have selected a set of variables, but now you can see that if it is an intelligent selection, you can, it's a variable that is collected to all. Okay. Now, this will come to the recent GraphCast type of situations. We did some transition probability calculations that if we have set of days here, how many are the set of days? So there are two things here. One is that some part of the days which I see that in the corner nodes are more stable node. By more stable means I am saying that a large number of days are associated with these clusters, and when once it is here, I calculate how many times it jumps to this all 9 pattern. What we find that is the jumping pattern follows a pattern, like there is a maximum probable transitions occurring from this pattern to this pattern. So this is a vertex which is stable, and from this vertex we are if you get this edge is much stronger transition than this. So in terms of graph approach, this is the most probable. So once I get a day which is clustered here, it is relatively easy to tell what is the most probable day for tomorrow. So this is a way of saying that, but this is a very coarse grain clustering. Okay, I'll go to the prediction part a little later, but this is what information it gives actually. Now, so what we did is, now we have to remember, I have shown you the EOF patterns of rainfall. I tried to say that, okay, my patterns are actually related to the EOFs of the pattern. So we did some mathematical transformation like this of the patterns here and here, and we are able to show that this matches with the EOF1. And additionally, other patterns are available which are actually not there in the linear which are equally important and which are not there in the linear EOF analysis based on rainfall. Okay, so I'll not go through these things, but what I am trying to say, if we plot the power spectra, we will get the principal components are following the interseasonal peaks, and it has the properties of the interseasonal oscillation. So based on these things, and if I increase the number of clusters, okay, so suppose we have a 3x3, 4x4, 5x5 clusters, you will see that the patterns are much better, and all if we take the number of, so if we try to match with the linear 8 patterns like what we do in the Wheeler and Hendon type of plot, you will find all of them corresponds. But when we have more number of patterns, this gives a rich number of structures. And how those, and each of this way, what we try to see is that 5x5 clusters, 4x5, all clusters give the monsoon intraseasonal oscillation. I'm not going to discuss with this because this has to be, this was related to the Wheeler and Hendon type of plot, which does the principal component based on this. But the take-home message is you get the UF patterns plus a set of additional patterns, which we did analysis for some years, which are very important. I'm not going to talk because this is not that physical aspects. So we are trying to tell that, yes, you can go from here to large number of patterns. Essentially, you are getting the similar geometry of the features, but you will get more. What more and how it is useful, I'll come. Same thing I did for MGO, okay? And what we are trying to, there we have used the diabetic heating, for example, and we find that first, this is, one is the linear Wheeler-Hendon mode, and this is the our clusters, which matches. But again, if we add more pattern, one thing I can show here, for example, that these are the some pattern, this dotted line is the pattern based on the Wheeler and Hendon, and this pattern we get from this clustering. One thing is the heating structure is much more stronger here. So heating structure is stronger. Now if you put a heating in the Matsuno-Gill type of problem, when you have stronger heating and when you have weaker heating, you will get lot of different results. If you see the circulations plotted there in this thing. So what I try to say is, MGO like monsoon inter both are derived empirically, and depending on how you are trying to cluster it and how you are trying to get the vertical profiles of heating, if this profile of heating is given, and that both will create different structures. Now, which one is MGO? Both are MGO, but the thing is, depending on the situations, some additional things. There are other papers which I am not showing, that upper level like maritime continent heating is different, many other places it's different. So the point is that empirical methods are very useful to construct the physical structures of the system, and when you get the heatings and other things, you will find the response of linear models are different. Like if you put a simple Gill-Matsuno type of equation and you put the different type of heating, you will get difference. So this helps. So this way it helps how it is different, how it is not difference. So we get feature extraction, pattern recognition, and dimensionality reduction. So naturally, I'll go to the prediction problem next. Okay. So this was last day's lecture. So today I am trying to go to the second part, and this is much less compared to last day, but still I'll show some more applications here. So prediction problem. This is the linear, somebody showed here that we have observed input up to this, and we have the forecast here, this. So in a prediction, simple autoregressive terms are there, moving average terms are there, so you can formulate from using this, either this, or you can formulate this. What machine learning model is doing is actually you are trying to remove these errors terms in such a way, optimize that these patterns become much more optimal, so the predictions become better. Okay, now so these are some time series properties. Okay, different trends, seasonality, extreme values, all these are properties of the time series. So I just continue that thing, that if I do a higher order graph or node, what we get a lot of different type of situations of intraseasonal oscillations. So this is the value for a particular date in this node, and then we go back and forth. So these are the lag and lead days here. The figure, it did not come. So what we are trying to say is that you are getting similar patterns in the similar corner. That is the point of the SOM. And if you go into the spatial patterns of those things, some of these node I have shown here, you get a similar, but lot of dissimilarities are there in the detailed spatial structure. So how to do a prediction of interseasonal oscillations? What we did is the analog. Yesterday, I think Dr. Ashish Chattopadhyay has told about it, that analog was I can say long invented, but then first principles model took up, and then now machine learning models are actually, again, we can help on those things. So what we have, there are, so you can see that these patterns persist up to long. So there are a lot of nodes of some patterns, one or two nodes there. So there are long range and short range. There are large scales and there are small scales. Patterns which have high variance, which have low variance. Also, you have signal and noise. And if you choose the change this thing to a say 2x2 or 4x4 or 22x4, there would be complex patterns. So you have to optimize all those things. So what we did that time was to predict the situations. We took one or two particular. So we took care of this long range and short range and large scale and this thing. Okay, these and these things are automatically taken care of, which we have not shown. But these two, once we take care of these things, what we did is we take a particular day, see which node it is, and then go back to my library of states, and based on some averaging method, we recreated the past pattern as the future evolution of those days. In the past 5 days, if my Euclidean distance from today to past 5 days is matching with a set of n number of days or closest, those days I take as the future evolution of those past days are taken as the evolution of the current day. And that time, so as I said that it was some clusters like this. So what we got, the result is like this. So this is a observed pattern like this, and this is the predicted pattern, and it shows a good correlation between this. And these are, of course, these are few years. Then later what we did is you can do some experiment with ensembling. So for example, uh, you can have some n number of patterns here. You can have change the number of input variables or the vector space. Okay, lot of experiments you can do, and you can generate a set of ensembles. And once we get the set of ensembles, we actually get a pattern. So this is pentad, means 5-day average. Another thing is interseasonal oscillation prediction. You do not predict what is going to be happen in the 20th day. Rather, you are going to predict what is going to happen between 17 to 22 days or 15 to 20 day average, like that. So these are called the pentad, or right now IMD gives a prediction of weekly average. So in the weekly average, you can get a, because decisions, it is related to decisions. I am going to take a decision where my decisions, I am not interested if I want to go on a 20th day from today in the field, but I would like to know that if the rainfall would be good in that week, so that I can arrange my whatever decision process, like arrange my farm or arrange the pesticide, whatever is this. So as we go to long range, the decision process also, it helps actually, because we are not getting the exact quantitative. So some way it's a trade-off between my decisions and what we actually get. So both things has to, it's a good thing. So we get some good correlations up to 4th pentad. Okay, that time it was a good. Now also it is a good. If you see the current prediction models, in the 4th week, it's all models have correlations in the range of 0.4 operational models. So now also it is good. Okay, so that is the prediction part. I'll come to some more examples where we have tried to use now more recent methods. These were used by simple prediction aspects. Now we are trying to look into physical aspects. Now all of you know El Nino, of course. So the physical aspects is El Nino and La Nina develops like this, and you have something called West Pacific, you have East Pacific and Central Pacific. The index of El Nino are developed based on West, East, Central Pacific. And the point what we are trying to ask is that, you know, the theory of El Nino, which was there, like Keynes-Zodiac type of model, where you generate the oscillations in the model. Okay, so that was those type of models in the 1980s were very successful because they generate the 5 years periodicity around 5. So what was learned there is the one theory of El Nino says that you have the depth of thermocline very weak in the Central Pacific, and once you give a perturbation there, you give a Rossby-Kelvin response. Okay, Kelvin wave propagates to the east, Rossby wave to the west, and then the thermocline deepens and you have a warm SST, and these Rossby waves reflect from the western coast, western side, Australia, Indonesia, and then it goes back. So there is a downwelling Kelvin wave, upwelling Kelvin wave. Those features are actually very important. Now the question what we are trying to ask here is, I say, like, the what side, which East or West Pacific takes a greater role in predicting the ENSO related patterns better. So in the sense I'm saying whether West Pacific is important for prediction or East Pacific is important for more important for prediction. So this is what we studied here is, for example, and you remember this thing. So the temperature equation is like this. You have a simple temperature tendency term, and you have these advection terms. These advection terms are based on spatial gradients. Okay, remember I said convolution neural networks always filters the spatial gradient. So once I do a convolution type of thing, this type of things is very easy, and del t by del t, it is the time in modern, based on what we have learned, we should use some type of transformer to get the long range relationship. But I thought that time, okay, let's not go there, because we have a feed forward multi MLP layer which will take care of the simple del t by del t evolution. So we thought that a vanilla CNN would be very easy for us to understand, because CNN will give you the surface SST patterns will go like this, and then you will have this temperature pattern. This is with the MLP. So what gives that pattern? So we thought that the CNN is one of the way to go there. So as I have discussed CNN with this, that there are different type of object like hat and human. So those things mixed together, they can actually, so if a pattern coming from a type of noise, then it will be filtered. We hope that it will filter as far as the, because in machine learning model, if it works, it's good. Okay, so if the filtering is done in the way, it is good. Otherwise, we don't care if it is good. Okay, so we did this. This is the architecture of the model. We did 3 experiments. One, we took the whole Pacific. Another, we took West Pacific, and another we took East Pacific. When we did we are calling control as where we have taken the whole Pacific and the West and this East. So what we did is, once we do the cluster, once we did it, and these are some of the training features which you can see in the paper itself. Okay, so what we find is that, first of all, this model is not giving you the physical barrier. You know, the ENSO has a physical, it is called spring predictability barrier. Okay, so if you go from January and if you are trying to predict the SSTs in June or July, it's very difficult, because spring comes and that time the predictability, due to this predictability barrier, that signal is lost. Okay, so this model does not outperform or does not give physically some answer to the spring barrier. So the spring barrier stays whatever model we choose. So in a way, that is comforting, that my model is not violating the physical constraints of a dynamical model. But in other way, from prediction perspective, it's depressing that, okay, it's not simple enough. Spring predictability barrier is not simply solvable using a CNN. Okay. So then what we did is we show the predictions. We generate a lot of ensembles because it can be done from CFS, and we have provided the PDF of the plots. Okay. So what I am trying to tell you here is that if you have a control experiment here, the take home message, lot of things I have kept, but the message here is that we find that the West Pacific experiments which are done, those West Pacific predictability are more close to the more predictability in the whole, if we take the domain. So East Pacific relatively gives less contribution to the prediction range, prediction skill, correlation skill for the long range. So the point is, if you have to design your buoy system, for example, where you will put, you will have to get the waves more good, more observations in the West Pacific than the East Pacific. This is one of the thing which that time we are thinking. So this is a way of optimizing your resources instead of putting everything in the all way. When you have to optimize your resources, you need to capture these Rossby waves, the reflections of those Rossby waves much better. We did some more experiments on that, but we are not going there. So the point I'm trying to tell here is that those experiments have given some physical insights from the CNN model. The other thing is, it's very important. People come up with every other day, my model is good, my model has a, in ENSO, I have seen papers claiming 24-month predictability of ENSO. Okay, where is the predictability barrier? I mean, spring predictability barrier. There is nothing there. The point is, if I do an ensemble of simulations, you will get a lot of, so you will get a spectrum of models which is low scale and some spectrum of model which is extremely high scale, even at a longer lead time. So if I cherry pick those subsets and I say that this is my model, it's simply you are overfitting some way or you are making fool of the people. Okay, so it's not like that, that if a model, just one model gives a better skill, does not mean that every instance when you are going to get that model running, it will give better skill. So this is why ensemble simulation and the showing of the results of ensemble simulation in a machine learning model is must. Otherwise, it can be easily told that, okay, you can cherry pick a few set of models which are very good and you discard this and then you come up with a weight vector, set of weight vector, but actually those models are overfitted, or even if it may not overfitted, there can be other things like those noises, because we start with a random initial condition, some way it has fixed in some directions that you are getting a better skill for this, but do not trust those things because those will not. So you always have to go in a ensemble mode of simulations. Otherwise, you yourself will not be sure your model's best skill and the worst skill. Okay. Sometimes practically it is not possible to run because machine learning models are very computationally accurate. But I am saying from a pure prediction perspective, when you are going to a user, your objective should be give a decision based on ensemble simulations rather than one specific or few model specific simulations. Okay. So I showed it, we showed it based on different El Nino events, La Nina events. Sometimes some El Ninos are very good for some ensemble and some ensemble at the longer lead time also we perform this. So the message here is the West Pacific gives a better skill compared to the East Pacific. If you take East Pacific and try to predict the Nino 3.4, by the way, the predictor here is Nino index, okay, then it is better you use a West Pacific than the East Pacific, okay. So these are all I have discussed, so I'm not going, okay. Now there are things like, I'll go from machine learning to how machine learning gives a impact-based forecasting, okay. So what, you know, heat waves, some applications were discussed by Professor Ravi. Okay, that these are, so sometimes temperature related definitions do not work with heat waves because it's the human impact which we are talking. And sometimes, suppose we have a day, series of days when you have temperatures 38, 38, 38. Even the next day it comes to 37.5. Still, you will find that that day the prediction you are meeting equally uncomfortable than this day. Now, why it happens? Because of the accumulated effect. So heat waves, impact on heat waves, there are studies from Australia which have shown the longer span of durations when a cumulative heat wave index is high, then it becomes more mortal than 1 or 2 day with excess high air. So because our body 1 or 2 days, 3 days responds well because our body's mechanism at least have this, but if it is accumulated, so even a low heat wave conditions which gets accumulated for a long time is equally dangerous than 1 or 2 day strong heat wave conditions. So that's what is importance of impact based forecasting. So that's what you are trying to do. Okay, so we developed some model based on a set of LSTM. This was a simple experiment because we are focusing on more on the impact side rather than develop. But we later developed other models, but we have not published it because it was anyway. So there were things we used a set of LSTM and we create set of ensembles based on LSTM. And what we did is instead of predicting temperature, we took excess heat factor. So excess heat factor is an index which is widely used in Australia, where we try to get two factors involved. One is the actual last 3-day temperature and last 30-day temperature. So last 30-day temperature component gives you the cumulative effect, which I have shown. And last 3-day temperature, you can think of it as an effect of the current situation. So it's based on how the last 30-day and last 3-day both, that is how it has the heat waves were means how they. So the point I'm trying to tell is that this is where this index is defined. So I am trying to predict it using this. And we try to get some, these are some details, we get good predictions, but again, these predictions when danger is not there. So this index, if it crosses 0, by definition, it has the heat wave like situation. This I have shown one grid point prediction location. So you can see many playtime when it is not dangerous, we are predicting good. Many times when it is dangerous, we are not predicting good. So actually, we could predict maximum up to 2 to 3 days. But even that is also good in terms of impact. But so what I'm trying to tell is, even your model is good if your model is trying to extreme value predictions. For many days, it will be good. For some days, when it is more crucial, it will not be good. So that's a very important thing. So for extreme value prediction. So what we did is we converted that thing to impact. So we find out, these are the predictions here. We find out the predictions where we have more dangerous conditions. So we convert that information to a risk. How did I convert? We took the thing that where there can be many ways. You can like you have a place where you have so suppose more people work in the field, for example, or you have more outdoor labor which is available from your socio-economic statistical data. You can convert the risk information from the heat wave there, or you have, but this is not done like that. We did it, but in the paper we reported just simply because if this index is high, and then we say that these are the districts which are having high heat wave risks. You can, so IMD's current strategy is yellow, orange, red. So we tried, because we are putting operationally for the first time, we did not go to the orange alert, more than orange alert that time. So this way you can convert your information to a impact information which was available in IMD. Okay, now this is a more compact version of it which I was telling. For example, this came, so it uses a large language model. So what it is saying is that, For example, the question is, okay, summarize the potential risk and benefit arising from climate change for growing wheat in so and so places. Okay, which has a location this, okay, the claim site is the thing. You see how the information is given. So they give your current and temperature, precipitation, wind, policy and regular implications, then recommendations. Okay, so what are the so this is based on a language model. So this is where you can go. Similarly, one simple another example is some crops in Nigeria. People are asking, okay, why summarize the potential growing different types of crops in some state place, Nigeria. Okay, so what is the best crop to grow here? Location this. So they gave the current climate evolution, then they gave the crop recommendation, then they give the risk. Okay, so the point here is you have a forecast as a scientist. You have ultimately this is where your forecast should land. If it does not land here, it is actually your benefits will not be fully explored by it, because prediction, if you are doing any other thing, is okay, but prediction as exercise is always better to go in land as an impact base. Yeah, 10 minutes, right? Sorry. Okay, let's. Okay, so these are the things. So I'll stop in the impact based here. I just want to go one slide with the graph cast that in the graph neural network, the same concept which we have used, they have used this thing. So what they have did is, this is a gridded representation. Then they have done a multi-mesh representations of the graph networks, and then they processed it with the graph network, and then just generated the forecast actually. So which we did on 8 to 10 parameter. Now it's 50,000 or some around that range of parameters. Okay, now the point here is, you see, they did not use the attention mechanism. So what they did is they did coarse to high resolution representation of the graphs. Okay, what I am trying to say here is that these resolutions, each resolutions derive different relationships, and then finally they get the forecast. And in the decoder, you are actually mixing that information and turning it back to the left. So that you see multiple patterns, long range interactions, and high spatial variability. These are the important things which I am seeing. Even if they are doing it in a large, high scalable manner and a fast manner, these are the most important things predicting, irrespective of the data, from language to vision to computer vision to meteorological data. Okay, so I think I will just touch one more thing. In the Pangu weather, they have used a transformer. They have not used this multi-mesh graph representation. They have used a transformer, which is called the swing transformer, where they have given the predictions. Now, I would like to show you, just study this thing. You will see that the predictions, even after doing all these things, more than 1, 2, 3 day extreme value predictions are still challenging better. So the last word is still not out. You are here to use those informations available. It's not only scalable information, it's only the scientific. If you want to add more science to it, you can add it and you can get it done. Okay. The latest ECMWF, for example, they have replaced that. Initially they are using GraphCast multi-mesh representation. Now they have replaced it. This is the latest. They have replaced it with a attention mechanism. Okay, so because they have used the Vaswani architecture, and they have used. So what I am trying to tell is, all forecast systems are now trying to use attention, or which is giving the temporal long range, or the CNN type of situations, which are giving swing transformer, for example, which are giving these things. So, okay, so I'll stop here. So few common message emerge. Attention transformer is promising. Large number of model available, but the long range forecast beyond weather. I have written 10 days, but it's 3 to 4 days is now the skill which you can go to the public. Simply and frank, public cannot be given more than 3 to 4 days skill as of now. And the means weather forecast. That's I'm not talking about seasonal or other things. The application of forecast is easier if we have impact-based AI. So that's where I stop here. Thanks.
Thank you, Dr. Rajib Chattopadhyay, for this talk in which you showed the details of the monsoon intraseasonal oscillations and also talked about the heat waves. And so, any questions from the audience?
Hello, so this is Rahul Kashyap from IIT Kharagpur. Thanks for the insightful talk. So for heat wave part, you showed data from 2000 to 2020.
Yeah.
And March to June or something like that.
Yeah.
2020 March to June was COVID lockdown period. That would have altered air quality and meteorological conditions.
Yes.
So did you take that into account, or it might potentially corrupt your long-term data?
No, we do not take into these things because IMD data was available because they are making graded data always. Okay, so even if during the COVID, so think it of another perspective, like pollution is doing this thing, but there are situations when other agents can also reduce the temperature. Okay, so pollution impacts. I mean, it's good for a machine learning model to learn from that scenario also. Okay, so it's the more diverse type of scenario you are getting, the more is the so physical speaking, temperature is del U del T plus the advection terms plus the other forcing, which is radiative forcing due to pollutions, which you are talking. Those pollutions are not there, but those have created a more diverse type of scenarios to learn from the model. Okay, because LSTM, what it does mechanistically is it puts a long-term past memory in these gates and it adds a local term. Okay, so I believe that has enriched the past data set for training rather than impeding these things. Okay, that's what as of now I have this, but I have not checked. Yes, I have not checked. I kept it up to 2020.
Thank you, sir.
Hi, sir. So for ENSO predictability, you were telling about filtering out the spatial gradients.
Yes.
So algorithms like POD and DMD, they also decompose spatial and temporal.
Yes.
So can't we use that or CNN?
Yes, you can use. If you think that it is taking care of those spatial variances, you can use that method. This I have used CNN because CNN is highly scalable. Okay, all other statistical methods, they do the same thing. But here we have the freedom of choosing a huge data. You can add multiple channels like lot of vertical levels easily without thinking about this thing. But yes, you can do it. I have seen papers doing those things, but yes, you can do it. Yes.
Thank you, sir.
Anyone else?
So you should you can outline a few patterns to predict the interseasonal oscillation. Like
Yes.
you had a set of patterns that you can recognize. But I was curious if similarly you can outline some set of patterns if you want to predict some type of extreme, like let's say rainfall extreme. So if you can outline some set of patterns that you can use as a proxy, on maybe not proxy, but directly as an activation function for some ML model.
Yes, so that's where I stopped actually. Some nodes in the SOM patterns are actually extreme patterns. What it is, it has to be done because now graph neural network become more popular. You train a graph pattern based on those nodes which has those extreme events, because rainfall has now 100 years of data. You have a lot of extreme patterns you'll get. Train a graph pattern like those nodes, and then so it comes under some pre-processing way. First you filter it with a topology preserving conservation, and then from there you go there and do additional training for the model, you can use. Yes, you can, but we did not do it. I have seen people trying similar methods like that, but yes, people have done it, studied it. You can do it in there.
Sir, I have a question regarding the feature selection using self-organizing map.
Yes.
So here you have shown that the clustering for Indian precipitation.
Yes.
So if I want to do the same thing for the global precipitation, so will it be applicable?
Yes, you can do it. You will recover the ITCZ. You will recover the those bands where West Pacific, where there are more rainfalls. You will recover the Indonesian region where there's a, even you will recover. For example, when I generated the MGO pattern, I took the global data around the tropics and I generated the rainfall all over the tropics there. Okay, yes, you can do it.
Thank you, sir.
Okay. So I think let's thank Dr. Rajib Chattopadhyay once again.